Lewis structures. Lewis structures are used in chemistry to represent how atoms connect to each other. There are two different methods by which we look at Lewis structures. We have ionic and we have covalent compounds. So Lewis structures differ for each of these. Now the way that I look at something being ionic or covalent depends upon a property called electronegativity. This is how much an electron wants to gain a bond, gain an electron in a bond. If I consider a tug of war between two atoms, the bond between them, I'm going to see how likely one side is to win that tug of war. The difference in electronegativity determines how likely this is to occur. Now, the electronegativity scale ranges from 0.7 to 4.0, which is arbitrary, and each atom has a specific electronegativity depending on its element. Things that are closer together in the periodic table tend to have smaller differences in electronegativity than things that are farther apart. I look at electronegativity difference and I can rank these and classify them accordingly. If the difference is less than or equal to 0.5, I call this nonpolar covalent. The term covalent, remember, refers to overlapping or sharing, valent, so sharing of valence electrons. If it is between 0.5 and 2.0, then it's polar covalent. If it is greater than or equal to 2.0, it's ionic. Now remember that ionic substances have charges in actual ions, whereas covalent substances do not. The term polar and nonpolar refers to whether or not there is a charge buildup on the molecule. Just like a magnet has a positive and negative end, a polar molecule has a positive and negative end. Looking at how these atoms come together then, we write Lewis symbols for the atoms. Those atoms that have specific electron configurations have specific Lewis symbols. And the way that G. and Lewis established this Lewis symbol configuration was that, for example, the main group valence electrons, all the valence shells are the outermost electrons. So we'll talk only about the main group elements in this because transition elements are a little bit more tricky. So looking at a diagram then, the three inner energy orbits here are inner shell electrons. The outermost orbit would be the valence electrons. The valence configuration for all the main group elements is ns2np6. So that means that that's the maximum configuration they can have. For the n value, that's the period they're in. For instance, sodium is in period 3. Argon is also in period 3. So if I take argon, which has the maximum number of electrons in its period for the valence shell, argon would have a configuration 3s2, 3p6. It has a total of 8 electrons, 2 from the s and 6 from the p. Sodium has a total electron configuration 1s2, 2s2, 2p6, 3s1, 3p0. That means that in its inner layers, in the first layer there are 2, in the second layer there are 8 from 2 plus 6, and in the outermost layer there is 1. Each s can hold 2, and each p can hold 6 because there are 3 different orbits that each hold 2. Sodium has a valence configuration then, not a total configuration, but a valence configuration of 3s1 with only 1 electron in the valence. I represent this using blanks. I fill only a single electron in, and so there's only 1 electron represented. Lewis symbols operate by taking the inner electrons in the nucleus and representing them using the elemental symbol. The valence electrons are then represented using dots on the outside. Lewis symbols are written as if a square is the elemental symbol. On the right hand side is the s, which holds 2 electrons, and on the other 3 sides are p's, each holding 2 electrons. I first fill the s and then one by one the p's. I put 1 electron per p until all 3 of the p's have 1 electron before I start to pair them because electrons repel each other. Looking at the main group elements then, sodium would have 1 dot on the right for its s. Magnesium would have 2 dots on the right, which would fill the s for magnesium. Aluminum would then begin to put 1 in the p. Silicon would put 1 in another p. Phosphorus would put 1 in the third p, and then we begin to pair electrons in the p orbitals going around with extra electrons. So sulfur gains 1 pair. Chlorine puts another one, so now it's got a total of 3 pairs. And argon would have a total of 4 pairs with 8 electrons total. I can make ionic Lewis symbols from these elemental symbols by working according to the number of electrons in the ion. Argon does not form ions, so we will exclude it. Moving then to looking at the main group ions for this period, sodium loses an electron, so there are no dots in its valence layer from the energy level we were looking at. So there are no dots total. It has a 1 plus charge, so we put a plus charge for the sodium. Magnesium also loses all of its outer layer electrons and gains a 2 plus charge. Aluminum would have a 3 plus charge. Silicon can either have a 3 plus or a 4 plus or a 4 minus. Silicon with a 4 plus would just look like the 3 others before it. So these first 4 are what we call isoelectronic. They have the same electron configuration. They have different charges because they've lost different numbers of electrons. As an anion, silicon has gained 4 electrons. Now, an ionic substance does not share electrons between atoms. So to represent all the electrons belong only to this atom, we use brackets on the outside, and the brackets are what represent the outer electrons, or the electrons belonging to that atom. A 4 minus charge completes the symbol. Moving into phosphorus, which would gain 3 electrons, it looks just like silicon but has a 3 minus charge. Sulfur has a 2 minus charge, and chlorine would have a 1 minus charge. And these last 4 would also be isoelectronic, since they all have the same electron configuration as well. Looking at how to build a Lewis structure then, taking Lewis symbols, we put them together and make structures. For an ionic substance, the electron transfer occurs, so from an atom that loses electrons to an atom that gains electrons, I wind up transferring electrons. If I look at this, I combine the elemental symbols together in the Lewis symbols. So if I look at sodium and chlorine, sodium starts with 1 electron, chlorine starts with 7. When I transfer the electrons and make ions, I transfer from sodium to chlorine. Sodium gains its ionic symbol, and chlorine gains its anionic symbol and becomes chloride. To make the Lewis structure, I just simply put these two together and I have sodium chloride. If I have more than one atom of that particular ion, then I use a subscript to indicate how many there are. Looking then at covalent substances are very different. Because covalent substances have shared electrons, we have both electrons that are owned by an atom and electrons that are bonded in a shared pair. The way that bonding occurs is 2 atoms begin to come together, and as their nuclei approach each other, the energy begins to decrease. At a certain point, I reach an energy minimum, and that is the distance that is bonding between the two. If I try to put the nuclei closer together, the energy begins to increase exponentially from there. There are 2 different types of covalent substances. We have covalent substances in which the bond between them is shared equally, which are nonpolar, and those in which the bond is shared unequally, which are polar. Covalent bonds are represented using lines. So a line between 2 atoms represents a covalent bond. If I have more than one bond, like a double bond or a triple bond, I represent it using multiple lines. So I use 2 or 3 lines to represent a multiple bond. Non-bonded electrons are used as paired dots, just like they are in ionic substances. For the 4 different substances below, hydrogen fluoride has a single bond in the molecule, one between hydrogen and fluorine. There are 3 lone pairs, all on fluorine, so there are 3 pairs of dots on fluorine. Hydrogen has no pairs of dots, because there are no lone pairs. Looking at the octet then, fluorine is satisfied because it counts each of the electrons in its unshared pairs, which is a total of 6, and then all the electrons in any bonds. In this case, there is 1 bond, so fluorine counts 2 from a bond and 6 from its unshared pairs, which gives it a total of 8. Hydrogen counts 2 from the bond, and so it has a total of 2, which is what it wants. All bonds are counted for each atom in the bond, so fluorine counts the bond and hydrogen counts the bond. The only thing that remains only for a single atom are the unshared pairs. Moving on to water. Water has 2 bonds total. Now there are not double bonds, they are bonds to separate atoms, but there are 2 bonds to the same oxygen. So oxygen has 2 sides filled up with bonds and 2 sides that are left with unshared pairs. Ammonia has 3 sides filled with bonds and 1 with unshared pairs, and methane has 4 sides that are bonded with no unshared pairs on the central atom. How to write a covalent structure then, we follow a series of rules. First we write the skeleton. The skeleton is the arrangement of the atoms in relation to each other. Hydrogen and fluorine are always written as terminal atoms. They're always on the end, on the outside. The least electronegative atom is generally written in the center. Carbon tends to bond between 1 and 4 atoms to itself. Nitrogen can make either 1 to 4 bonds as well, while usually it will only make 3. On occasion it will make 1, but that's even more rare. Oxygen will bond 1 to 3, but usually only 2. Now you'll find oxygen will bond to itself only in cases where it's oxygen or ozone, O2 and O3, or in cases of superoxides and peroxides, which look like O2 with charges. Ternary oxyacids, which are the acids that are made from oxyanions, have hydrogen that is bonded to oxygen rather than to the central atom in most cases. In any molecule where I have multiple central atoms, I will write the most symmetrical skeleton that I can find. So looking at an example, let's look at the nitrate ion, NO3-. I would write the skeleton with the nitrogen in the center and 3 oxygens on the outside. After writing the skeleton, I will then begin to calculate the total number of electrons. I calculate how many come from the valence of each atom in the molecule, and then add an electron for every negative charge and subtract one for every positive charge. In this case, nitrate has 1-, so looking at the calculation, nitrogen contributes 5 for every nitrogen, of which there are 1, so a total of 5. Oxygen contributes 6 for every oxygen, of which there are 3, so a total of 18. If I add these together, there are 23 from the valence of the atoms. Now, since nitrate is a negative ion, I add 1, and I get a total of 24. After I've calculated the total number of electrons, I bond atoms together. I put a single bond between every atom connecting the molecule, and then I add electrons to the terminal atoms. And that will fill up all of the electrons that I have available. If I don't fill all the electrons by putting them on the terminal atoms, if I reach my octet and I still have leftovers, then I'll put them on the central atom. So in this case, I bond the nitrogen to all of the oxygens, then add the remaining 18 electrons to the terminal atoms. This creates a nitrate that has all of the electrons used, 6 for the bonds, 18 for the lone pairs, which is a total of 24. Next I check valences. So looking at the valence, oxygen counts 2 for every lone pair and 6 for the bonds, so all 3 oxygens are the same. Each has 3 lone pairs, which is 6, and a bond, which is 2, which is a total of 8. Nitrogen has only 3 bonds, which is a total of 6, so in this case nitrogen is unsatisfied. If it is unsatisfied, I begin to make multiple bonds. I take a lone pair off a terminal atom and make it as a multiple bond between that terminal atom and the central atom. In this case, I would pick an oxygen, take off a lone pair, and make a double bond to the nitrogen. Lastly, I would check my formal charges. I want to make sure that the overall charge of the molecule is the proper charge. I do this by counting for every atom all of its lone pairs and 1 electron from every bond. So if I have 2 bonds, that's 2 electrons, 1 bond, 1 electron, 1 lone pair, 2 electrons. I compare this to the number that started with the valence, so oxygen started with 6, nitrogen started with 5. If I take the top left and the top right oxygens, which are both the same, I get 2 from every lone pair, which is 6, and 1 from each bond, which is 1. So it's a total of 7. The bottom oxygen has 2 from each lone pair, which is 4, and 1 from each bond, which is 2, so a total of 6. Nitrogen has no lone pairs, and it gets 1 from each bond, which is a total of 4. Comparing that to the valence, nitrogen started with 5, now has 4, which gives it a positive charge because it's lost 1. The bottom oxygen started with 6 and still has 6, so it has no charge. And the top 2 oxygens, top left and top right, both started with 6 and now have 7, so each has a negative charge. In the end then, I wind up with a negative on each of the top left and a positive on the nitrogen. The net charge on the molecule then, 1 positive cancels the 1 negative, and a single negative remains uncancelled, giving the molecule 1- overall, which is what nitrate is supposed to have. Steps then in writing Lewis structures. The first thing we do is figure out what the chemical formula is and what Lewis symbols are involved. Next, we have to identify whether the substance is ionic or covalent. After that, I use the proper convention, either ionic or covalent convention. I look to make sure the octet is satisfied, and then I look to make sure the charges are satisfied. Now, looking at the convention, I cannot mix up conventions. If I have, for instance, an ionic substance, I will not put a bonded line between the atoms like this. For a covalent substance, I will not put brackets around things that have lone pairs. So neither the top nor the bottom of these structures is proper because I put a line for an ionic substance on the top and brackets on a covalent substance in the bottom.